Hi everyone. So we're gonna get started now. So we're very excited to have Kyle as our next speaker. Kyle is a research scientist at the Allen Institute for AI, and he's an expert in natural language processing and machine learning research in general. So please join me in welcoming him, and he's going to be talking about language modeling recipes.
Cool. Test, test. Hello. Hi. All right. Hey, everyone. Thanks for making it back after lunch. Yeah, I'm going to talk about language models. I may be well-versed in text, but I'm not well-versed in like science models. And so the hope is I'm going to present, luckily, a more of a takes type of talk, maybe like some hot takes type talk, very little math, very easy to digest while you're digesting your food. But hopefully you'll see some parallels in how I approach text and building language models for text, and maybe draw on some of these ideas for your own particular models. All right, let's get started. Feel free to interrupt at any time. We can keep it fairly light. Just as a little primer, I'm assuming everyone here has the fundamentals for deep learning, but maybe not the fundamentals for text. So this is just a little bit of primer on some details that are kind of important to understand what's going on. I'm going to assume that everyone is familiar with concepts like learning rate schedulers, Adam W, batch size transformers, like these types of things necessary for training machine learning models, that you're familiar with core language model concepts. You've heard things like next order prediction, tokenization, sequence length, stuff like that. You know what PyTorch is. I'll have a couple of snippets of code. Don't try to run them. They don't actually work. But the key to understanding text, if you're building on your foundation of understanding deep learning and transformers, is to look at what the input and output of these models looks like. So if your input is something like a little question, like this string here, you toss it into your model, and then you get some sort of string out, like a next word completion that gives you your answer completed on the original string. Okay, so this is all fine. We know how these models work. We've played with them before. But actuality, let's look a little closer at what actually happens here. So when you have your string, like Sewon described earlier, this passes through a tokenizer, which turns your string into something like this, just a bunch of numbers. These numbers are basic indices that index into your input embedding matrix, which turns your entire thing into tensors. And once you're in tensor land, we know how everything works. This is all standard deep learning. We're happy. So as a summary, just understand that to go from text to tensors, you're working with tokenizers to transform things, and tensors roughly have some dimension of batch size times sequence length times your embedding dimension. Let's look at outputs. How outputs work. How does a model actually get to this type of string output? Well, again, your model is outputting logits because everything's in tensor land, going through a bunch of operations, and you get logits. Once you get logits that look something like this, you take some sort of argmax to figure out what is the highest logit, and that gives you indices, which then you again look through the reverse index of your tokenizer, and that gives you the string. So just as long as you carry on your tokenizer and your embedding matrix, you should be able to go seamlessly between tensors, input output, to strings, which is kind of where's we can actually interpret what these models are doing. All right, summary, your tensors at the end look like batch size times sequence length times et cetera, same thing, and you use your tokenizer. Besides this, everything should be super familiar to what you're used to. Training code looks kind of like this. You input the dimensions of your tensors, everything looks as like standard training code. That's it. That's all the primer you needed. Now everything else from here should be hopefully pretty straightforward. I'm going to walk in this talk through the stages of training a language model. At a high level, you can think of it as two big stages. The literature seems to have coalesced around these two big stages. We're going to call them pre-training and adaptation. Sometimes adaptation is called post-training. Pre-training is really about this phase where you're trying to imbue this model, train a model that has some ability to understand natural language. It acquires a lot of knowledge, develops a lot of core skills, capabilities to be able to do stuff. It's not really a usable model, but that's sort of the foundation of what, like when you think of the foundation model, this is what pre-training gets you. When you think about adaptation, this is when you develop your model so that it can follow user instructions, avoid harmful behaviors, respond to human preferences, and refine the core skills that were instilled in the pre-training phase. For pre-training, nowadays, actually, people think about these as like, there's actually numerous stages to training. I'm going to simplify this and consider this to be 2 stages of training. Base model training typically looks something like this. If you follow what's happening with the learning rate, usually you have a little bit of warm-up, or for like 2,000 steps, let's say. So less than 10 billion tokens worth of training, up to some sort of maximum. Commonly, you'll see something like a decay. These days, you have fancy learning rate schedulers that are like that have like infinite, just like stable learning rate and flat up top. But nevertheless, it's basically you incur trillions of tokens worth of training during this phase, and then at the end of your this long phase of training, you do some sort of linear decay of your learning rate down to 0 over a short amount of time, such as 50 billion tokens, let's say. These, colloquially, we call these pre-training and mid-training. I know we're never actually training. We're only either pre or post-training. And so pre-training, you can really think of it as this is 99% of your training budget. Trillions of tokens. When you hear like Quen models trained on 18 trillion tokens, it's like this is where most of it goes. And mid-training is typically only about 1% of the training budget, timed with this phase where you're decaying your learning rate down to 0. And I'll talk a little bit more about like what the implications of this are. On the adaptation side, well, you don't have two stages, you kind of have 3 stages. There's 3 dominant techniques for adaptation. You have, and they kind of flow in this order. Once you have your base model, you go through supervised fine-tuning. This is your traditional fine-tuning. This is where you teach the model to different types of task formats, how to follow instructions. It just makes it more usable. More recently, techniques such as preference fine-tuning have emerged. This is when you align these models to steer towards outputs that align with human preferences. You get a little small bump in capabilities as well. And then in reinforcement fine-tuning, this is like reinforcement learning with verifiable rewards, if you're familiar with this. This is a really hot area that's really exploded in the last couple of years or so. And this is where you pick particular tasks for which you have some sort of way of automatically verifying the correctness of this task. And then you do RL, like in almost like a traditional RL sense on this to really boost performance. So this is where a lot of the fancy code reasoning or like math reasoning models emerge as they emerge through this type of phase. Cool. That's it. That's all the basics. And we're going to get into each of these 3 phases of training, data, and adaptation from here. Any questions before I start? All right, cool. Please interrupt if you'd like. All right, let's start with training, pre-training, let's say. Architectural choices, I'm actually not going to talk about them. Go see someone's slides. She did a great job. So let's move on. I'm going to talk about some almost like basic fundamentals about how to approach your training that you might not see written down in any paper anywhere. This is how we think about pre-training. Pre-training is a super high risk operation. And so one of the core things you want to focus on is how to figure out how to monitor the health of your pre-training run. Good modeling decisions, architectural choices, training like configurations prevents training failures. Here's examples from really expensive wasted training runs that we've done in our group. On the left is an example of if you watch training loss just slowly go up, you can see all the multiple restarts where we tried to change something, and even though it helped for a little bit, loss would eventually diverge and go back up again. This is a completely separate training run where we had one wrong configuration. I think it was on weight embeddings, and that blue curve just never picked up downstream performance. And we didn't discover this until almost like a trillion tokens in. These are super costly mistakes. Here's a rough estimate. So I'm kind of estimating at about $2 an hour for a single H100. That's if you buy like a giant cluster and you kind of price it out roughly. This is like a fairly cheap cost. And even under this fairly cheap cost, a 7 billion parameter model, 1 billion parameter model, these feel like really tiny models. You're seeing like 30 billion or 70 billion or 100 billion models these days. Even for these tiny models, a failed run can cost you hundreds of thousands of dollars, which is why we really want to avoid cases like this. So this is what we should monitor. My advice for what things to monitor. Obviously, we want to monitor things such as downstream performance, monitor loss to catch cases such as this when it's happening. That's great, but look at this particular run. This particular run looks great. Downstream performance is going up, perfectly fine. This is if you actually watch the gradient norm, like looking at the model internals. This is what was happening under the hood. It was really, really, really spiky and steadily increasing over the course of this. Now, the issue with this is we found much later, like I think like 3 or 4 trillion tokens in, that this is a sign of a really unhealthy run. Gradient norm spikes are a precursor to eventual loss spikes, such as the one over here. So this is like tip for find cases of like metrics that you can monitor that maybe are hidden by your downstream metrics, by your loss, that are an indicator that maybe there's something wrong with your run. You might want to stop it, change something, or even restart your run altogether. So in summary, spikes are an indicator of eventual divergence, is the common knowledge. So try to detect these as soon as possible. I'm gonna talk to you about 2 dominant, yes. Whether it's, I think there's 2 different hypotheses. I don't fully know. There's one hypothesis that I've heard thrown around, which is your model will eventually diverge no matter what you do. And so the hope is that within your training budget, you try to mitigate, like make architectural changes and training changes such that the model will spike and diverge after you're like completed your, like you pushed it out far enough so that you've completed your training before that happens. I've heard that hypothesis. I've heard another hypothesis, which is that you just keep improving, let's keep hill climbing and keep making them run more stable. I don't know which one's true because there's not enough like examples of really long runs, but often these things aren't discovered until quite a bit long after your training run has started. It's also not like a deterministic thing. It's more like oh, this is one of the things that seems heavily correlated with eventually, if your gradient norm is spiking, eventually then your loss will start spiking. And then after that, eventually your loss will start diverging. Is that sort of, okay. There's 2 types of spikes that we look out for when we're training. We call them colloquially fast spikes and slow spikes. Fast spikes are stuff on the left. We don't care about fast spikes. They're kind of annoying, but they eventually resolve themselves within some batches. Slow spikes are the stuff on the right. This completely destroys your training run. As you can see, it's just not going to recover from here. So gradient norms are a way of indicating that we want to avoid slow spikes and not get distracted by fast spikes. Here are some examples of things that we've done in the past to fix this. Stability is really the key. It's a key here. Think about initialization. So when you initialize your model, there are some rules of thumb. I also have on these slides that hopefully everyone has access to. There's like each of these things has like a reference to the paper that describes everything. So I'm just giving you the bullet points here. Please read their papers. They're great papers if you want to know more. But stability for initialization, there's some rules of thumb of like properties of a good initialization that you want to maintain. For example, the scale of activations and the gradient should remain roughly the same from layer to layer. Scale of activations gradient should scale mostly with the model width. There's some formulas on how they should scale together. So you can see an example of our terrible run and our better run, where we just implemented this idea from this paper. Our old run is in blue and our new run is in orange. We trained this for a very long time with this idea from this paper, and our run is much more stable. Eventually, all those spikes in blue no longer occurred in our training run. So we're very happy with this initialization. Another example, I'll kind of gloss over this, but kind of what Sewon was saying is like architectural choices. A lot of these choices are very hard to explore, but some of these are actually quite consequential. For example, the use of RMS norm, which Sewon mentioned earlier, is pretty standard now. But also you can do things like manipulate the order in which layer norm occurs in your architecture. These also have some positive benefits for stability. And finally, weight decay. This is a common practice. I've seen some papers that use weight decay, some papers that don't use weight decay on embeddings. What we found is that if you have very, very small token embeddings, this can cause instability eventually. We removed weight decay, even though this seemed like it was counter to traditional machine learning logic. And then based on the results we're seeing here, we also got more stability. This isn't like the comprehensive list of like, you need to understand these fixes. This is just more to illustrate that this is the process in which we try to stabilize runs. when we're trying to make these architectural changes or these training changes, it's basically make one change, run it for a long period of time, and look specifically for whether your gradient norms stop spiking, whether your loss stops spiking. Yes. It's a different normalization. Yeah. Cool. All right. Now, oh yeah, totally. Yes. Not really. No. Sorry, I don't really know. I've poked through. I thought once thought it was data, and I poked through the data. When these fast spikes happen, it's hard to tell. Most of the data looks kind of sensible, and I've seen problematic data for which it doesn't spike on, and vice versa. It's actually really hard to tell because it also depends on the resolution. Like a lot of these spikes visually, if you show different researchers the same plot, they might interpret these things as fast spikes or slow spikes or whatever. It's a little bit of alchemy and intuition. I think it's like a pretty green research space as to actually how to make very good decisions around this. Right now, it's a little bit of an art. Yeah. Yeah, exactly. A lot of this is just empirical based. Yeah. Yes. Oh, wow. Okay, there. Yeah. Yeah, I think for our latest language model, we developed our own initialization, custom initialization, which was quite a bit better from like the Xavier initialization that we were using before. I can't tell you why. I think the person who developed it had some intuitions around like, oh, it needs to be like the weights need to be normally distributed around something. But at the end of the day, it's empirical. Like it's hard to know until you try it. I think the Swiglu paper had this amazing quote. Oh, I should have kept it in the slides. The Swiglu paper had this amazing quote for like after presenting this is like, I think the quote was, we have no idea how we have no way to attribute like why these architectures work other than to divine benevolence. And like, that's kind of the feeling a little bit is you just try. Yes. Okay. I'll get into a little bit with this next section about that. Yeah. Yes. I think it's just activations go up, right? I think it's just like growing activations. A lot of it's just like standard with ML deep learning 101. Like as you like train a model, certain types of embeddings start to grow, certain types of activations start to grow roughly in magnitude. This is why we add norms everywhere to try to keep things under control. But if you add too many norms, then the model fails to learn. So I think it's really just like a balancing act. It's almost like just like engineering alchemy to keep everything stable. We didn't normalize enough, or we didn't add some other, like Z loss helped. I forgot to add a slide about Z loss. That was another regularizer to keep things under control. Maybe, I'm not sure. I haven't seen, I had to dig a little bit more into it. We could chat after. I'm not sure. Yeah. Cool. Okay, I'm gonna move on to experimentation. See, maybe this will help. The big thing that really helps us out when we're making decisions here, because unfortunate reality is that so many things are not that intuitive. I think you talk to different ML researchers and they'll completely disagree. I've talked to 2 people doing long context research about rope, and both of them have written seminal works about rope extensions, and both of them completely disagreed about whether you should go larger radial, like the theta should be larger or should be smaller in general. So like I think even the experts in this field definitely intuition is pretty contentious. And so at the end of the day, experimentation is your friend. The problem here is, like I said before, experimentation is really expensive. It's really expensive to train these large runs. So what is the tool that we actually rely on? I think if you're training these large language models, you have to rely on scaling laws. Like this is the #1 thing you invest in for your modeling practices. There's plenty of works on scaling laws. I'm not going to go into how they work. They're actually fairly simple up to some details on execution. But here's an example of how one works. The idea is that models behave fairly stably if you're looking at the parameters, the levers that you tune are amount of training tokens, amount of parameters, model size. You can, like 1 billion parameter models, you could have more layers, fewer layers, larger layers, whatever. But at the end of the day, it seems like this tokens times model size or flops is really the big factor that decides the performance of model, and performance model is really well captured by the loss. So on the left-hand side, if you train a bunch of small models, let's say 100 million parameter models, or even smaller, I've gone down to like 30 million parameter models, at varying amounts of data, varying amounts of sizes, you should be able to literally import like SciPy, curve fit, plot your loss, plot your configurations, such as your tokens or your flops, and try to fit curves to this. And the goal here is to basically fit curves such that if you hold out some points, you have a high accuracy of prediction. So some of those examples of prediction numbers here, 1.3% error for our fit curve to what we actually observed. If you have a very, very accurate predictor of loss, given what you've chosen for your model size or an amount of tokens, what you can do then is make changes to your model architecture, train small models, and increasingly grow the size of the model and the amount of tokens that you put into your experiments. And as you grow the pool of the size of models, you keep refitting the curves. And if you, over time, you gain some confidence that like the change that you made, the architectural change or training change you made, is mostly anticipates some type of eventual loss if you were to scale it for the full thing, which you don't have enough budget to do too many runs of. You do have to eventually try these bigger runs. But the hope is that you spend most of your budget on the really small models, some of your budget on the medium-sized models, occasionally do the larger models, and then you only pull once for your final biggest training run through these predictions. If you're worried not just about loss, but you also believe you want to understand downstream performance, the middle curve is an example of how actually it's fairly practical to fit a curve that predicts, that basically regresses between your final downstream task performance and your loss. Generally, lower loss tends to correlate well with better performance on some model. I'll show some cases where it breaks later on at some different slides, but if you chain these two things together, you should be able to see curves at the ends like this, which is I include more compute expenditure into my model with my current chosen configurations, and I should anticipate as I scale the model up that this translates to how much downstream performance. And if you're happy with that result, then you can go ahead and with your modeling choice. If you're not happy with the result, then you keep iterating at the small model scale. Cool. That's it. That's the number one thing. Just try to squeeze as much value of the compute you have by deriving as much value from small models as possible through scaling laws. Yes. Ah. Yeah, so it's not know nothing. It's we started with previous scaling law papers, but there's two papers I cite here. I think one of them is, I think they all kind of disagree with each other. What I've generally learned is that scaling laws, the specific parameterization of a scaling law is really tough to transfer between institutions, between organizations, between like kind of model families. There's so many little details that goes into the implementation of these models that you're probably not going to get exactly the same scaling law that someone else found onto yours. But the process in which you derive a scaling law is generally well tested, and I think it's pretty easy to follow that practice. So my recommendation is generally find your own scaling laws that work for your own institution. For us, in our case, we still did things in terms of number of tokens and model parameters because those are the common parameters. And then we had like we iterated on the parametric form to really get it to work for us. Yeah. Yes. Yeah, so we don't try to do a full scaling law. This is it's for certain types of hyperparameters where it's been proven before, you use something like mu-p. I think mu-p is a good way of picking hyperparameters that transfer across a lot of configurations without having to induce the full scaling law like experimentation load. For other parameters where you don't really know, often what we do is we just follow this practice. So standard scaling law practice that shows up in a lot of papers is pretty impractical. It might take like between 1 to 10% of your final training run. Nobody has that compute to expend on that. for every little change you're trying to make. Like you saw set one's like slide, like that was like all these possible little tiny differences, and we don't know which ones will cause a breakage in the model. So instead, what I generally recommend is like some sort of decision process, like a sequential process. So you start with your small models, you prove things out of small model. If you see something is good at the small model scale, then you upgrade. And you can upgrade first through amount of tokens. So train your small model up to like 1x chinchilla multiplier. That's like basically number of parameters times 20. That's how many tokens. It's like a nice rule of thumb. If it works there, do like 3. If it works there, do like 5. If it works there, do like 10. If you're happy with it at that small scale, upgrade to another scale, repeat. And at some point, you either start eliminating the idea or like you keep going with it. But as you accumulate these runs, you have enough data points to start fitting these curves. And you can see how these curves change as a function of like these repeat experiments. If it's very, very hard to fit curves, we tend to have a lot of hesitancy around this idea. It's like something's going wrong. This is like untested territory. And if you have an easy time fitting the curves, then, and each time you're fitting the curve, you run the next run, you have low prediction error, then you generally have a lot more confidence in your decision. Cool. All right. Oh, that was the wrong slide. Okay, final takeaways. This was the whole training section. In summary, minimize the number of modeling training choices you have to make. Again, training is super, super expensive. If you can get away with it by just looking at what other people have done and following them, you should definitely do it because there's so many other things that are worth testing already. Avoid catastrophic training failure, like the stuff that we incurred, by monitoring loss and downstream metrics, but not just this, monitoring modern internals such as grad norm, embedding norm. There's generally best practices on these things should not be growing too high, should not be spiking, should not get too small, etc. So you can use these as kind of more early signal tests. And finally, implement as many techniques as you can to improve training stability. Finally, invest in scaling loss, invest in your tiny, cheap experimentation setup so that you can make these decisions without blowing your entire compute budget. Cool. Any final thoughts before I get into data? Is kind of the big heft of the talk. But all right, let's get into data. This is probably going to be some stuff that people haven't really seen before. But let's look at data. Actually, I don't know how many people have actually opened up language modeling data and looked at what it looks like. But let's open up some data. Pretty easy these days. Here's an example of data from Wikipedia. There's some metadata, yes, like you see like versions and IDs, whatever. But for the most part, it's just a giant string. This is what we toss into the model before it gets turned into tensors, like I showed earlier. But what's really interesting is structured data also is just treated as a giant string. So look at this. This is a question answering data set. It's curated with a very particular structure, which is like question in all caps, colon, something, hypothesis, colon, something. And then like multiple choice options are shown in this particular fashion. And the model has to solve this. The thing is, with language model training, pre-training phase, we don't impose any type of structure in the data as a result of training. We basically take whatever data as exists and we pretty much toss it in this format. This changes later on in later stages changes, but as of now, everything is just plain text. There's 3 big themes for data. I'm gonna call these are the cats for people who are sleeping. Now time to wake up. There's 3 big themes that I like to think about when you think about data. You want to think about how to get data. You want to download the data onto your machines so you're ready. So it's like you're shopping for data. You want to transform the data in some way. You want to make it good. So it's like cooking the data. And then at some point, you actually have to see if the data is any good. And so that's like experimentation or trying or tasting the data that you've actually created. All right. So these are 3 big themes of data curation. I'm going to go through each of these 3, mostly talk about the general practices for each. For acquisition, here's my little 2x2 table of the common ways that people acquire data. So on the left-hand side, on the rows, basically indicate you can basically crawl data. That's the dominant way people have heard about crawling. Or you can curate data yourself. And by crawling data, nobody wants to crawl like write up your own crawler. So for the most part, you download data that other people have crawled and they make available to you. So Common Crawl is an example of an organization that professionally has been crawling the internet for decades, I think. And they make their data available through a bulk API. You can just go download it for free. Or you can decide not to do that and write your own crawler spin up your scrapey Selenium chops and try to crawl yourself. And in terms of the curated content case, curated content is usually thought of as like task-specific data or data for a very specific purpose. Let's say if you want to do like scientific QA, that would be like task-specific data. You can, again, download it for others because other people have curated this data. So you can go to like a repository like Hugging Face or go to GitHub and people can have shared this data before, or you can create it yourself. And create it yourself could be going out to collect it yourself manually. But often these days, the common idea is to generate it synthetically. So synthetic data is a big topic for curating your own data. All right, so these are the common patterns. Let's see what people actually do in practice. So what I did is I surveyed every major data set that has been publicly reported what sources they used and has been proven to train a successful language model on top of it. So because there's a lot of data sets out there that haven't been proven to actually successfully train a language model before. And the thing that you'll notice is that Common Crawl shows up a ton. In fact, it's almost the same names that are showing up for each of these major data sets. Their upstream source seems like it's the same sources they're repeating. So let's actually look at this. This is a breakdown of how many tokens have been contributed for different upstream sources to the creation of these data sets on average. This is plotted on a log scale, because if I didn't plot this on a log scale, you wouldn't see those other bars. Common Crawl is 99% of all of the tokens that you get. It's a single source of failure for all of your data needs. If you actually decompose this, let's look at like APIs. Anything that's APIs, surely GitHub should have thousands of GitHub repos for you to pull from. PubMed, Archive, these are like giant repositories of data. Wikipedia, isn't Wikipedia massive? Let's actually look at this again on log scale. Common Crawl as a web scraper still presents nearly 80 to 100% of the data that most people use to train language models. These publishers for like scientific papers or content platforms like Wikipedia, really small percentage of the data actually comes from them. So just a good thing to note that we're super reliant as a field on basically one entity to provide all of our data needs. No, Common Crawl is free. Yeah, Common Crawl is free. Why don't we do other stuff? Like, I guess, like, why aren't we curating, why aren't we crawling it ourselves? Why aren't we generating synthetic data? Why aren't we collecting more task-specific data? And the answer really is cost. It's extremely hard to crawl the internet yourself. There's a lot of JavaScript out there. You need years and years of experience to know how to write a crawler, especially now that there's a lot of anti-AI bots blocking traffic. And the crawling ecosystem has been really complex. It's really difficult to get to the scale of Common Crawl, which is why most people rely on them. Why not synthetic data? Synthetic data is really expensive. We're talking about pre-training. Pre-training requires trillions of tokens. To generate 1 trillion tokens using GPT-4o API, I think I needed over $1 million to generate that. And that's to test out one idea. What if I want to change the prompt and I need to retry things? Synthetic data is extremely difficult to scale. So this is why we rely on crawling. To really understand this, let's think about the tension between data objectives. These are the things that everyone complains about when you work on data. You'll have the people who are constantly thinking, we need more and more scale. We need as much data as possible. The super big, I want to train the giant model. And then you have the people who are thinking, I need super high quality data. I don't want all of this internet web junk, the best data possible. And so you have this tension between scale and quality, because as you get higher and higher scale, data is not IID. If you want to get more scale, you're going to dip into some pockets of data that are pretty not very interesting and not very nice. But necessary, and the flip side is if you want really high quality data, you're going to have to throw away a lot of data. It's very hard to get high scale, high quality data. So these two are in contention. This is general best practices, not a proven empirical thing, just something that's generally we've learned as a course of working on this is you don't actually have infinite scale for your compute. Most people have a sense of, I have this much compute I can actually use. I have this model that I want to actually train. And so as a result of this, you can solve backwards for how much compute and therefore how much tokens you can actually really realistically use for your big training run, even budgeting out all of your experimentation that I said you need to allocate for. Common rule of thumb is 1-to-1. If you're training a model with X amount of compute, that's your final big run, you need about X amount of compute just reserved for experimentation, because there's going to be bugs, there's going to be all sorts of little things you need to try out. right? So that basically gives you exactly how much scale you should worry about. So you don't have to worry about infinite scaling of your data. And from there, you also want to think about scale is another factor to limit the scale that you really have to consider is you don't want training runs to go on forever. One of the biggest failure modes for pre-training is that pre-training takes too long. Your entire team is just waiting. Your cluster is burning for 3 months straight and you can't do anything else. And if you go for too long, because the world is changing really quickly, by the time the model has finished training in 90 days, maybe you don't even care about this model anymore because everyone has moved on to another thing. So it's actually really practical to just consider how long are you willing to wait and do nothing else but just monitor this training run with your entire team, such that at the end of it, that you still actually want that artifact and you're robust to changes. So some groups do like 30-day training runs. Our group does 45-day training runs, but you have some sense of like temporal constraint. And then once you fix take into account all these factors to constrain what you actually want for scale, then you maximize quality. And this gives you a nice, really simple framework for managing these two data tensions. Now, I'm going to go back to this. I'm going to go back to this figure because if you're managing these two data tensions, and as we saw, there's ways to get a ton of data through Common Crawl, through crawling. And then, but what about my like really special, I have like this really focused task. I really want the language model to do this long-tailed like coding language that's not crawlable on Common Crawl. So how do I deal with this like small amount of data that's really high quality for the task I want, weighed against the really large scale kind of junky data that I'm grabbing from giant crawlers? How do I manage these two things? Well, here's a really elegant way you can manage these two things. If you think about what pre-training is doing, pre-training in these two phases, there's a natural way to slot this data, this imbalance of data between the high scale and the high quality. If pre-training is really about using as much data close to your compute budget, and mid-training is about the high quality stuff, you can basically think about mid-training is where you stuff in all of the high quality data, your supervised fine-tuning data, your synthetic data, your like painstakingly curated data. It's data that isn't enough in quantity to use for pre-training because the signal would get washed out. You want to put it later on in training because these models have very strong recency biases. Things that early on learned in training gets forgotten over time. So as an example of this, your super large scale data sets, stuff you get from Common Crawl, let's say GitHub has like 400 billion tokens worth of stuff, Reddit, et cetera. They go in pre-training, and then maybe you find a subset of this data that's the really high quality subset. You'll keep that around and then mix in some stuff that maybe you wrote a crawler specifically for Stack Exchange. And then that's where you want to put it because it's a really small amount of data. Maybe you generated some synthetic data, you download some data sets from Hugging Face, you need to know where to put it, you put it in mid-training. This also gives you a really practical way to approach this because again, pre-training takes a really long time. And so are you doing nothing for 45 days while your training run is going? You're probably also curating data. So what if 30 days into your training, new data lands, someone else on your team has created new data, what do you do with it? You don't want to throw away your entire pre-training run. So leaning into this idea that pre-training is a really lengthy process and you need to anticipate the fact the world changes, such as you might get new data. You can add in new data near the end of training and find some way so that you can smooth out this transition between data, anticipate data shifts in your overall pre-training strategy. So this is kind of like data curriculum, but not data curriculum motivated by better performance at the end. This is data curriculum because of practical real world considerations. Cool. All right, this is how to manage getting data and knowing what to do with it. Let's talk about transforming that data or like cooking that data. There's three big themes in transforming data. You can think of them as linearization, filtering, and mixing. I'm going to go through each one of these really quickly. Linearization is something that people don't really think about too much. People have generally thought about it as filtering, but I really want to cover linearization because it's pretty important. Linearization is this process of taking the stuff on the left-hand side, which is how we consume the internet. Text, yes, it's text, but text is documents are 2D. There's visual, there's layout information, there's graphics interwoven. I know how to process this because when I look on the thing on the left-hand side, it makes sense to me. And the right-hand side is what the model sees. Let's go into this a little bit deeper. Linearization is still the process of like basically flattening these documents. So you'll still have preservation of content, such as the title on the left still shows up in the flattened text, the linearized text on the right. The main content is still preserved there. But because visually, I can process what's on the left-hand side. And so when I read a document like on the left-hand side, I can skip everything that's navigational content. when you linearize the content, or basically when you flatten these types of 2D documents, all of this other stuff also shows up in these documents. And there's no particular indicator that this is junky text or not useful prose to the language model. All of this, again, the language model just sees everything as one giant plain text file. This isn't also something where you can like, oh, I'm going to build some rules so I can filter all this ad stuff and navigational stuff. It's just actually an open question around what is the correct way to flatten or linearize text that fundamentally is structured. So on the left-hand side is a paper, 2-column paper. And if you look at figure 3, the caption, it kind of interrupts the prose. So where is that supposed to go? Like what is the left to right plain text reading order for this? What about tables? How should they be structured? Do I need to inject special tokens to actually properly linearize this? Or because there's no white space, like I can't just use white space tokens necessarily to represent this. Here's another example of like figures, diagrams, these like this like left-hand sidebar thing. Do we include that type of stuff? Do I include the page number, etc.? These are all choices that happen at linearization time when you turn your documents into plain text fundamentally. And this is an open question as to how to do this correctly. But let's say that you've managed to decide some way to flatten your data, to linearize it. Then it's about filtering. I'm not going to go into too much detail. There's a ton of works about how to do filtering. But filtering generally is when you take what you've painstakingly acquired and scraped and you throw most of it out. What you throw out is stuff that you generally develop these pipelines for throwing out various things. Let's go through some of them. You might want to throw out toxic content on the internet. You don't want to see any of this. Maybe you have some personal identifiable information. Like it's actually pretty easy for people who work on vision models. It's actually really easy to accidentally scrape people's like uploaded images of passports and their like social security cards and stuff like that are uploaded to various sites. So just like if you look into your data enough, you'll find these types of instances occurring as well. So maybe you want to filter all this out before you train. Duplicate data. How many copies of the US Constitution do you really need until the models kind of picked up the value from it? So intuitively, generally intuitively and also empirically, people have found that filtering out duplicate data means that you're spending your flops, your training compute on net new data. And so generally, if you want to see more diverse data, removing duplicates is a good idea. And low quality content. There's so much of the internet, it looks like this. It's like navigational pages, search sites that are just saved. Nobody really engages with this like sensible prose, but it is text. But like this has very little like learning value when you put it into a language model. Here's an example of like stuff you might want to throw out. So here's a training run for which we had all these spikes. I think somebody asked the question like, what's going on intuitively with the spikes? So I'm going to go into what I did here was I picked one of these spikes. I think it was the green one. And I looked at what was the batch that this was spiking on. And in one case, I found something really interesting. There's a documents from this subreddit called R Microwave Gang. And in this subreddit, this entire subreddit is full of posts of people posting like it's a humming sound, and then all the responses are like beep, because like the microwave's done. So hyper entertaining, people engage with this, but the actual like usefulness for training, it's actually kind of not useful. In fact, it's a little bit bad because it's correlated with spikes, not deterministically, but like occasionally you'll find stuff like this. So if you inspect your data often, you'll catch cases like this, and then you can write regular expressions for like, oh yeah, if you have like the letter M 40 times in a row throughout this entire document. Data cleaning is a never-ending process. Here's an example which this idea of like scale hides noise in your data or imperfections in your data. What I did here was I trained exactly the same data set, exactly the same training order, 2 different models, one at a 7 billion parameter scale and one at 13 billion parameter scale. And this is just looking at training loss. And when I thought this data was really, really clean, looking at the 7 billion parameter model, at the 13 billion parameter, I started getting spikes. And if you inspect those, not deterministically, but on average, I started finding more and more issues that, oh, I should write another regular expression for this. So there's always going to be more and more problems. And as you scale up, you're going to start dealing with, I thought my data was fine. I thought my data was fine. And you forget to revisit your data. There's always more things that get basically turned up because you're scaling up your model. Yes. So this one, I went to that batch. That's a particular step. And at that step, it's like a global batch size for us was like 2 million. So like sequences of 4K, batch size of 1K, like you just start opening up files and then you like, and then, yeah, but this is a common thing. You just open up files and you scroll through them on your terminal, just like keep sampling until you find stuff. Yeah. Yes. It's too expensive. It's probably too expensive. Yeah. Yeah. Like it's like the time it takes to develop that language model, you could have just written another regular expression and then moved onto something else. Or even to run it. Let's say if you want to run it online. If you want to run it, you're spending you need compute to actually run that inference while you're training. You could have spent the compute training a bigger model or just training that same model longer, which will give you better performance. So you always have this trade-off of like, I can have fancy technique for doing something, or I could have used all the energy and put it into my big model again. Yes. This is all one epoch. This is all one epoch. Yeah, it hasn't seen it yet. There's other issues when you start doing multiple epoch repetition. You might see some like step function thing in the loss. Yeah, I don't have any slides on this, but that would be cool. That would have been cool to show. Yeah. All of these are one epoch. Yep. All of these have been one epoch. Yes. Yes. This is why curriculum is really hard to nail down in this sense. Curriculum has generally worked out for us in this sense. Oh, wow. Maybe I shouldn't have scrolled back. But in this sense, right? There's like practical data curriculum. It does late stage domain upsampling for the stuff that's high quality, generally works out. But when you start getting finer grain to like instance level or batch level, like this dynamic decision making, one, you're incurring this extra cost on your clusters to make this change, which you could have just poured all the energy into just training more. And two, it's not deterministic. It's not a necessary guarantee that you're going to catch these cases. If you just replay the data another way, there's plenty of those microwave examples or similar examples that are in non-spiking batches, for example. So I think of it as like propensity for spike. Yes. I don't even think this was a finished run. I think this was like a snapshot of some run. But yeah, generally one epoch takes like 45 days. Whoa, okay. I think yes. Okay. They're related. I'll get back to fine tuning. Yeah, at a later thing. But they're very similar, I would say. I would think of mid training as like a smoothing process. A lot of the data they use for fine tuning actually shows up in mid training. So you can think of mid training as like kind of 50-50 mix between what you see at pre training and what you're gonna do at your fine tuning time. You want this little middle phase. It just helps with like transition. Sorry. Yes. Okay. It's a random sampling of all the data. We generally clean and ship data in phases. So let's say if you do a 2-stage training, like what I showed before, like pre-training and mid-training, then I'll clean everything and ship it once for pre-training. Once it's going for pre-training, I don't touch it anymore. I just let the model run. I monitor it for the issues in case we have to eject the entire RUD and revisit it. But when we do that, we're basically restarting the whole thing, reshipping a new batch of data. But then we'll work on mid-training data during that time while we're waiting for it. Once we ship mid-training data, transition mid-training data, then we'll work on SF, like fine-tuning data, et cetera. If you have a K stage, like say a 3 or 4 stage training, which seems typical nowadays with these really long training runs, you might do your data curation in these batches, but you never have like asynchronous constantly iterating on it, probably mostly for like teammates' mental health. Like it's like sometimes it's good to just like get data out and run things through and really see what's going on and then just move on to the next phase, move on to the next phase. You're always filtering out data. Yeah. In general, you always, how do I say this? There's a section about filtering that I'll come back to you about, and that'll explain a little bit. Yeah, but you're always throwing out a bunch of data. I always have more data to train for longer, but it might not necessarily be a good choice. For example, our OMO 1 was trained on 2 trillion tokens. Our OMO 1 point something in April was trained on 1.6 trillion tokens. And it was like 24 points better on MMLU than the first one because we just didn't clean enough. So by throwing out more data, we actually got a lot more boost and we trained for less. Okay, here's a rule of thumb for if you want to do this type of common sense, opening up files on your terminal and just constantly staring at stuff until you form some theories. Here's a rule of thumb that could be helpful for you so you don't get sucked into infinite data cleaning. I think about on the y-axis is the rate at which you're opening up files and you're finding obvious problems. On the x-axis is the amount of effort it takes to find these obvious problems. So when you open up any of this data the first time, you're going to find a ton of easy cases. Stuff that's just not even language, like it's like ad spam. Stuff that no human would reasonably engage with. This is really easy to filter out. So I would do a bunch of cleaning here, filter this out, keep sampling, keep filtering it out, writing rules to do this. At some point, you're going to find also a whole bunch of pornography, a whole bunch of toxic tests. This is pretty obvious. You kind of know it when you see it. It's really obvious. Write rules, write filters to clean this data out. As you're doing this iteration, eventually you'll catch yourself doing this thing where you're going, I think this data is fine. It might be useful for something, but I wish it would be better if it was formatted this way, or it might be better if that's when you cut it off. Everything on the left-hand side is really easy to work with if intuitively, write intuitive filters to catch most of these cases. But everything on the right-hand side, what I've generally found is that intuition kind of goes out the window and you have to experiment in the same way we have to do that experimentation with all the modeling choices. Stuff that I generally think as like, oh, meaningful, useful content doesn't necessarily translate to after a language model trains on it, it has the best behavior. It's at the end of the day, it's an empirical decision. I'm gonna actually skip this part. This part's fine. All right, let's move on. Okay. How much filtering generally happens? Here's examples from 2 different data sets. They kind of interestingly arrived at the similar filtering rate. I've seen everything between 50x reductions to 100x reductions from starting from total crawl pool to something that's really small and focused for your training. So kind of expect similar order of magnitude where you're throwing almost everything out. Let's talk about filters. I think I'll touch on your question around filters. So the issue with filtering and how do you define models and procedures for doing this type of filtering is this. The problem here is as you're building these filters and building these sophisticated pipelines and rules for throwing out content, the problem is the pipeline steps aren't independent. And I'll show you an example where they're not independent. And as a result of this, we also found that generally large, expensive models are really, really good for data transformation, data filtering, et cetera, but they're really, really expensive. You just can't afford to run a 70 billion parameter model at this scale. So how do we manage this? So first, I'm going to show you how linearization and downstream filtering interact with each other. On the left-hand side is data as distributed by Common Crawl. Common Crawl crawls these websites and represents these websites, the raw HTML, in a file format called work, which is basically, think of it as like a pure HTML representation, throwing out a bunch of JavaScript stuff. But it also distributes a file that's just plain text called a wet file, which strips out all the HTML tags and stuff like that. This was developed for web, like for people to build like search engines back 20 or so years ago, not for people to train language models. So if you actually open up one of these web files, you'll find stuff like this, where the text is really choppy, a bunch of new lines. It's essentially stuff, linearized content that I don't necessarily want to train on. On the right-hand side is another open source tool that can do this type of conversion. And the text is way nicer. The DCLM folks did an A/B test, basically training on the left versus on the right, exact same documents, and they got like 1 or 2 points performance improvements just such switching to this different tool alone. 1 or 2 points is pretty big within this space. PDFs, a lot more models are using PDFs. I think Quen3 said that they trained on a large pool of PDFs. PDFs require a different type of processing. PDFs require OCR, let's say. But then if you run any OCR tool, you'll look at stuff like this, random symbols, words that are hallucinated, footnotes are scrambled in there. In fact, what I did was I took the same document on the left-hand side and ran through, actually I ran through 11, but I couldn't fit in the slide, different open source OCR tools and looked at the output. And they give you really, really different output. Now, this is the problem. They give you really different output for fundamentally the same type of content. But if you run these quality classifiers, these filters on it, depending on which tool you used for the exact same content, it might get classified as high quality or it might get classified as low quality. And this is where it gets really complex, which is if you have a really bad linearization in the stage 1, it'll affect all the downstream filtering that you do. You'll tune things differently. And then if you improve your OCR tool, if you improve your linearization, you have to redo all the work that you did for your quality filter. So intuitively, the thing that you might think is, oh, well, I should spend really big money making sure I have the best OCR tool in the beginning, making sure I linearize with a really expensive model, so I get it right. So I get a high quality linearization from the beginning and all of my upstream pipeline steps so that I don't affect my downstream stuff. This is the tension, I guess, with data curation. I'm going to show you where that type of thinking kind of fails. Here's another example where we're doing personal information filtering. Bunch of examples of personal information that you might not want to train on, but you need to identify in your data first. On the right-hand side is the precision of identifying this type of content if I just write a bunch of regular expressions. On the left-hand side is like a tool provided by Microsoft called Presidio. It needs a key to access. I think there's a paid service for using it. It's a pretty expensive tool. It is better though. Look, it's a higher precision filter. It catches a whole bunch of stuff. Maybe I should use this really expensive, most powerful tool so that I don't affect any sort of downstream things when I'm doing my data transformation. The problem is I did the math on this, and this would have cost $5 million to run all of my pre-training data through once. And I don't have $5 million to do this. And this is, again, the tension between I have these giant pipeline steps and they all affect each other downstream. So I really want to invest in the best tool possible to do work. And yet I don't necessarily have the money to scale these large tools. So what is the secret? The secret is try to favor ideas for doing this type of data transformation, data filtering that allows you to scale to the large models, to large data size, and allows for frequent rapid iteration. I'll give you an example. You don't need to use 7 billion parameter models. You don't need to use like 70 billion parameter models. You can use a linear model like fast text. Fast text costs like $600 on some random EC2 instances that you can get to process all of Common Crawl. BERT, considered a small model, takes like $10,000 and you still need 64 H100s to process this. I'm not even giving you the math for like a 7 billion parameter model. That is the costs start going through the roof if you want to process Common Crawl. The thing about this is if you have the budget to experiment to run fast text, it's more likely that you're probably going to have a bug or you're going to have some issue with the large model that you only get to try once to run over your full corpus, as opposed to maybe with fast text, if I restrict myself to these small classifiers, I can try this 20, 30, 100 times before I even make a dent into my total budget. And during that course of time, I will probably find some hyperparameter, some configuration, some way of training these models such that it actually performs just as well as using one of these more powerful models. And generally, this has generally held to be true. Fast text, if you read the Llama 3 report, the Gemma report, et cetera, most of these model developers use fast text as well. All right, so that's filtering, transformation. The idea here really just being invest in things that scale. And finally, transformation under the topic of mixing. Data mixing is a really hot topic. If you were at iClear this last cycle, there's like 3 papers presented in the same session, all on data mixing. It was kind of interesting to see. But data mixing is this idea of like rebalancing your data. So let's say if you're training a code model, such as what I have here. Oh, it's kind of fuzzy. It's too bad you can't see it. The left-hand bar is Java. The second bar is Markdown. On the black bars are just the natural frequency that exists in the corpus. So naturally, a lot of Java code exists on GitHub. A lot of Markdown exists in GitHub, as you expect from READMEs. And so not a lot of Go and Ruby code out there. And so mixing might do something such as, oh, I don't need that much Java. I can downsample how much Java code I need to learn and upsample some of these longer tail languages that I don't have as much data. And by upsampling, you kind of just mean repeating that data. Now I'm going to explain, I think there was a question, it was a little related to this. I'm going to explain how mixing interacts with this quality classifier. When you're building these quality classifiers to filter data out in that previous section, the way you generally do this is you define a bunch of data that you label as positive. That's like the high quality stuff, your good stuff. And you define a bunch of data that you don't like. That's your negative stuff. Some people have done basically like educational versus non-educational. Some people have done their high quality stuff, and then you do like a random sample of other documents and you treat them as negative. So whether you're doing more like this or less like this, you're just training a linear classifier like flash text on your positive and negative label samples. So standard, very basic ML 101. But this is the limitation of that approach. Remember this question around, well, what about the scale of data? If I train a classic classifier and I essentially score my data and it produces quality scores from 1 all the way down to 0, and you can have it induce this ranking over your documents, is this threshold actually a tunable parameter? Can I actually just do a cutoff and say, oh, I'm going to take everything above this quality, and that'll be my high quality set? The problem is it's not really a tunable parameter because you're bound by how many tokens you actually want to train on. You can experiment a little bit with like training on less, but in general, training on more tokens on average tends to be better. And so this isn't a real tunable parameter because the real parameter that you're bound by is like, I need 6 trillion tokens or I need 15 trillion tokens to train on. So this is kind of the limitation in quality filtering, is like quality filtering as a single axis doesn't have enough degrees of freedom to meet your token budget. Now, let's think about beyond quality filtering. Well, the only issue here is I just had one axis. What if you decompose the data into a whole bunch of different pockets and just label things based on what they might be? And so an example of this is like, I'm going to taxonomize documents into how tutorial are they, or how politics are they, or how sciencey are they, or how health are they. This suddenly gives you a lot of flexibility, or what I consider to be like high degrees of freedom to optimize for how you select your data. When you have something like this, that basically segments, understands the composition of your data, segments it, and ranks and orders it, you can select the top portion of the tutorial data. You can select the middle portion of science data, et cetera, et cetera. High degrees of freedom procedures generally afford you a lot more way to squeeze quality out of your data. And so empirically, you can see this is what's happening. On the left-hand side is the natural distribution over these topics. If you didn't do any upsampling, downsampling, you just looked at what's generally on Common Crawl. Generally on Common Crawl, a lot of entertainment data on the left, a lot of personal blogs on the right. If you use quality classifiers as developed by most people in that single fashion, in that brute force fashion, you'll see that what they're doing implicitly in quality filtering is actually doing a selection of what types of topics of content they think is valuable. So you'll see with this procedure, the science and technology bar on the left-hand side, under FineWeb and DCLM, which are different quality classifiers, the science and technology set gets upsampled a lot. It's considered higher quality, so you pick more of it. But it doesn't go all the way. If you actually define a whole bunch of axes like a dot here, and you really tune this because it's a higher degree of freedom procedure, you'll see that this procedure, this one called regmix, which is, you can look it up. It's just like a procedure for really fine-tuning these mixtures over these like multiple axes. You'll see it pushes the science and technology even further than what can be achieved by just a simple brute force quality classifier. So quality classifiers implicitly are trying to do this type of domain selection, but they're just not powerful enough because they're a single linear model doing a single ranking, and you just don't have enough room to really filter. So, and this idea is like, you can actually layer a lot of these things together. So quality filters like those from FineWeb and DCLM, they provide performance boosts if you filter according to them. But if you add on these types of other mixtures, you can still see further improvements. So the idea here should be, as you're cleaning your data, do the simple basic stuff, filter things out, and start layering on more powerful techniques, more and more degrees of freedom. And hopefully they start stacking on top of each other, because the more complex procedures obviously probably take the more expensive compute. And so you don't want to use them all at the beginning when you're first starting out. Cool. That was data transformation. I know there's a lot. That was like the hefty piece of it. If you have, yes. All of this applies for any sort of language. These are like kind of core fundamentals. Now the specific implementation and how you use it will be different. So for example, if you want to train multi-language models, you probably can't rely on Common Crawl that much. Common Crawl is mostly English language crawls. I think there'd be a higher reliance on trying to crawl your own data if you wanted to train in particular specific languages, would be an example. But generally the same principles around crawling or not crawling apply. Yes. I can self-plug, but we developed an open source OCR tool called OmoCR. OmoCR. Yeah. I can share the link. I guess, yeah, I didn't include a slide on it, but we released this recently. The tagline is, we basically found a way to generate a bunch of data from GPT-4, which is really expensive. I think GPT-4 costs about $6,000 to process 1 million pages. So if you want to do 1 million pages and then get to like 1 trillion tokens worth for pre-training, this would cost millions of dollars to process everything through GPT-4. Plus, you'd have to send your PDFs to another company, and I don't know if you want to do that. OmoCR is synthetic data fine-tune. It's a distillation procedure where we fine-tune a VLM just to do this OCR thing. And then we optimize it with like SGLang or and a bunch of rules. And overall, you can process the same amount of PDFs in like $200 US. And it's all like open source, so you can download it yourself. Yeah, it's state of the art right now. So if you want to check it out, yeah, I think it's better than a lot of like OCR tools that people are charging money for. So yeah, cool. Yes. Very little. Google Books is actually very difficult to acquire unless you're at Google. I think there was a big effort from Harvard to release public domain books, which was very, very cool. So that was good. But up until that point, there was very little actual availability of like public domain or like digitized books that people could actually use for training. Most content, like I showed before, most content is basically web page crawls from Common Crawl. I think there's like if you're working within like the open source space, there's a really severe lack of like diverse scientific books, textbooks, and these types of things. If you want to train language models, you kind of have to go buy it or find other ways of partnering with libraries to do it or something like that. Cool. Experimentation. Again, the thing that when intuition goes out the window and you just have to try stuff, at the end of the day, experimentation rules. So experimentation, not all experiments look great like this. This was a really great experiment. We thought we were making a ton of progress. We're like train these tiny 1 billion parameter models, training on 4 different data mixes, only for a short amount of tokens. We can see that the purple curve is way better than the baseline. We're like, the purple idea is the best idea. We're going to go for that. As we use this technique a lot more, where we change the data, but we fix the model and only work with small models, we started realizing some issues. An example of an issue is this. This is a model trained, the same model trained on a whole bunch of different data mixes and evaluated on a benchmark called MMLU. And I have no idea which data is better. A lot of experiments look more like this than like this. It's inconclusive. So yes, it was a very cheap experimental procedure. I only spent a day and a half training on 16 H100s, but then I didn't get any result. I have no idea how to interpret this. And the reason for that is because when you train a language model from scratch, you're incurring maybe like a third of that training is spent in this uninformative phase, where if you actually play with the model during this phase, it's not even doing language at that point. It's just like trying to figure out how to stitch words together that are coherent. And so you spend a bunch of time on this uninformative phase where maybe by the time you finish your experiment, it had just started to pick up some signal on how to do this task, but you already concluded your training run at this point in time. It would have been nice if I trained for longer, but too late, I already launched my job and now my job is wasted. So what if we could just skip this early phase? Can we start from model that's already pretty good? That's pretty sensible. And yes, the idea is yes. So there's these things called annealing style experiments. And this was used in the Databricks paper and also in like Llama 3 introduced this idea. We tested it out ourselves, it's quite good. And it's these like what we call annealing style experiments, where we take a model that's already partially trained. It doesn't have to be trained to trillion tokens. Sometimes we just take like one that's been trained to like 500 billion tokens or 1 trillion tokens, a partially trained model. We switch data A, data B, and we just train on this, taking the learning rate down to 0. Almost like we are doing mid-training, just simulating the process of mid-training. And the hope here is that if we conclude that data A is better than data B at at this late stage time, does that mean that data A is the better processing for using at pre-training time? This requires some validation, but in general, we found this to be true. So this then gives you this idea of that there exists for every single experiment decision you want to make, there exists some experimental protocol that you can be very cheap, but it has to still work to at least reveal some signal. You have to break through essentially what's called the noise floor before, otherwise you're not observing anything. So to compare these two procedures on exactly the same data mix, the same data mixes, yes, what we saw on the left-hand side was a cheaper experiment, but I didn't conclude anything. On the right-hand side, I trained for longer. It took me 3.5 days on 16 H100s, but I started from a 7 billion parameter model, trained for a short amount of time. It did cost me much more, but at least I get to tell what's going on in my metrics. And so this is an example of like, invest in your experimental protocols, whether you're doing pre-training or whether you're doing data. There's some minimal cheap experiment that you really have to figure out what the right configuration is. So final takeaways for the data section, and then I have a very short adaptation section. Acquisition, fix your scale, then optimize the quality. Good rule of thumb. Crawlers, big crawler data like Common Crawl, good for pre-training. And your small, high-quality data that you painstakingly either generate synthetically or you curate, good for mid-training. When you're transforming your data, don't forget linearization. Everyone forgets linearization. They think about filtering, which is the big hot topic. Linearization can really ruin downstream filtering. Manually inspect your data often. You might catch other fun memes like the microwave example. Filter your data aggressively throughout a lot of it. And invest in techniques that can actually scale to your corpus. Don't rely on giant models that you can never actually run. Finally, higher degree of freedom techniques and transformations allow for more room for optimization, but they are also more expensive. So don't start with them, do all the common sense stuff, then invest more and more into these more powerful techniques. And finally, with experimentation, intuition works to a certain extent, always be experimenting. And in order to enable this and not blow all of your compute budget, you need to find your minimal experimental unit. Cool. I think I have just a little bit more time, right? 10 minutes? Okay, cool. Last thing on adaptation, this is actually a fairly fast section because it's a pretty hot area of research. So the fundamentals there's not as much fundamentals that I can really confidently say yet. Adaptation. As a reminder, since this was many slides ago, let's remind ourselves what adaptation actually is for. There's 3 stages in adaptation: supervised fine-tuning, preference fine-tuning, and then reinforcement fine-tuning. And they roughly, basically, supervised fine-tuning teaches instructions, formats, preference fine-tuning aligns to preferences, and then reinforcement learning is really about boosting performance on verifiable tasks. I'm going to go through each of these really quickly. The role of supervised fine-tuning. This is actually kind of interesting. So remember the example that I had before, which is like everything is just unstructured text? This is where structure comes back in. Most models today, the way we use them requires structure in the output of the text. So if you've ever played with GPT or whatever, then you'll see that there's things like system prompts versus where you have to you can type something in system prompts. There's like the user portion of text. There's also the assistant portion of text. If you have a multi-turn chat conversation, then you need some structured format to represent multiple turns, who's talking, etc. If you're doing agent type research or code execution tool use type research, you need special Sentinel tokens that your software has to parse so that it knows to shell out to some other like code executor. And so as we get closer to, as we get to adaptation, we need to inject these special tokens that are like wrappers around these AI systems can actually parse to do some other thing. And hence, that's fundamentally what structure is. Pre-training never considered structure, but now this is the time to consider structure. And this is what I mean by like chat templates. When people hear chat templates, usually they mean these types of templates or format. Usually they're talking about this type of formatting. How important is this? This is an experiment I ran this morning while this is going on. So I just made this figure. On the left-hand side are just 2 examples of the performance of models. If you did this annealing phase, just like do a little bit of continued pre-training without any supervised fine-tuning data, just using pre-training data. Just using pre-training data, in general, you get this much performance on tasks like MMLU. These are base language model pre-training tasks. But if you look at the black or the gray plots, once you start evaluating those language models on exactly the same tasks, exactly the same instances, but formatted differently, formatted using these strings such as, oh, but also, add chain of thought, or also don't forget to answer with one of these options. With reasoning chains, sometimes you can add a prompt that says like, oh, and also don't forget to step through your reasoning, like explain your reasoning, as do this step by step. Just adding these different prompts over the exactly same sample, you'll get performance differences like this, where a model that hasn't been trained on the supervised fine-tuning format data will absolutely collapse once you switch the prompt format, like we see in the gray. And if you add even just a little bit of this like templated structured data in your fine-tuning phase, that's when you start getting the performance recovery, which is what you see on the pink. It's not a full recovery because I didn't finish training on this. This was just like a little tiny run. This is like 5 billion tokens only. So a lot of supervised fine-tuning is really about this formatting piece, injecting format. In general, what we do is we do these experiments where we just basically monitor a whole bunch of runs, and we keep injecting more and more supervised fine-tuning data over diverse tasks. And we look for cases when we start plateauing our performance. So generally, you keep getting a lot of performance improvements. See, these bars all have this like sloping upwards to the right-hand side. You get performance improvements across a number of tasks, and at some point you saturate tasks because you've learned enough of the format, and that's kind of, you're done with that benchmark. Supervised tuning, how much do you actually need? You need a ton of data. You need as much general chat instruction data as possible, combined with targeted skills such as like coding or math or whatever you want to focus on. Common practices nowadays seems like you need like 1 million examples. And these are 1 million examples with different prompts, fundamentally, with their associated answers to do supervised fine-tuning. How do you actually do that, though? It's really hard to get this. Well, techniques these days lean a lot on synthetic data, where you start with a small amount of human-curated data. You do some fancy process that essentially allows you to take that human-curated data and rewrite a paraphrase with it through a more powerful model like GPT or Llama or something. You'll clean out any bad generations, and then you repeat this loop. You just keep repeating this loop until the model saturates, or you start noticing some degradation in your performance because it's collapsing, and you stop. But in general, this is a pretty open space of exploration. The idea here is that models are improving really rapidly, so you don't have to do a lot in this step anymore to get good responses. The key really here is to start with some good set of human seed prompts. Another way you could generate more diversity in these through synthetic protocols is to add things like personas. So a lot of prompts look like this, where you have something that says, oh, this is a persona of a person who might prompt you for information. And you might have something like constraints, and also the output has to satisfy these constraints. Personas are really great. They inject natural variation. Given the same task, if you write it for a doctor versus a moving company driver versus a chemical kinetics researcher, you just get different output. It's a way of injecting variability in your model outputs, in your these synthetic data examples. And constraints also can help fine-grain instruction following. So here's an example of types of constraints you can just artificially put in your prompts, as long as you can verify that the output is correct. This is free supervision. So you can say don't include these keywords and randomly select these keywords, or answer with at least these N words, at most these N words, and then you can automatically verify that this is true. That's supervised fine-tuning. The data looks very similar to the data that's in mid-training. I think that was your question. Once you're finished your supervised tuning, you basically have a model that you should be able to play with. You should be able to interact with it. Preference fine-tuning comes at this stage. Preference fine-tuning is pretty much known to just be good for style and chat evaluations. It makes us like to use the model a lot more. It doesn't really help capabilities that much. So not going to worry about this math, but generally the classical way of doing preference fine-tuning back in the day was through PPL or reinforcement learning with human feedback. You basically optimize for some reward under some constraint that you don't want to rely too much on the reward model. The classical pipeline for doing this, ignoring the math here, was you start with your base model. Let's say it's gone through supervised fine-tuning, or start your pre-trained model. You do supervised fine-tuning. You use the supervised fine-tuning to collect human preference data. You generate data with it. You prompt it, get output, and go get it labeled. Once you get it labeled, you build a reward model. A reward model, I think that was presented in this morning. Those are the same type of reward models that take in two outputs and score them. And then you do something like PPO to actually get to your line model using the reward model. This was the old way of doing things because it really depends on how well your reward model works. There's a lot of complex tasks that can't be accurately modeled by reward model. So what if we just don't work with reward models, just like ignore them completely? This was a very cool idea called DPO. DPO is excellent. As you kind of see, the theme of this talk is favorite things that are intuitive and very simple, allow you to iterate fast. DPO, the code is right there. Super easy to write. This removes a lot of problems around how to scale these things, how to work with larger models. It's effectively implicitly training reward model, but it's just bug-free in general. Most of the community has moved on to DPO because it's just easier to work with. And in practice, yes, PPO does give you better performance, but like negligibly compared to the practical realities of like, you could do a lot more with DPO, you could iterate a lot faster with DPO. Again, how do you scale to millions of preference pairs to train these models? This is when you deal with, okay, so I can have humans judge pairs of outputs and then collect data this way, or I can have LLMs judge, and this is like LLM as judge as a paradigm. Most of the frontier labs do a combination of human data extensively combined with synthetic data. In open research, practically nobody really has the budget to do large-scale human preference data, and so most of it is done with synthetic data. An example of pricing is one LLM as judge label costs about $0.01. I think on the market, one human data point costs like $5 to $20. So you can think of like human data fulfills this purpose of high noise because you don't have a lot of it, but very low bias because it's really capturing what humans actually want because they're really humans. Synthetic data has very low noise. You can control these processes using LLMs as judge, but there tends to be high bias because they're already biased towards their own output or biased towards particular model developer's choice. And finally, the new hot topic in the field is reinforcement learning. This is called reinforcement learning with verifiable rewards. It's basically used to boost math reasoning, coding reasoning skills, tasks that you can actually automatically build a verifier for. This is your standard RL pipeline, your loop. Don't worry too much about it. Just look at training data goes in, you have some agent that's basically generating completions, and you have a reward model scoring. So this is what's been done for the RLHF before. What verifiable rewards does is it takes this reward model and go, I don't need this thing. I just need to know if this is correct. So just give me a 1 if this is correct, if my code generator was correct, or if my math solve was correct, and 0 otherwise. And you can do RL on this. In fact, this is basically classical RL with ground truth rewards from the environment. Why is it different? It's actually not different. I know it's another term that's being thrown on in NLP, but it's basically exactly the same thing. The reason why it's thought of as a different thing is because there's a lot of implementation details that actually is necessary to get it to work. An example is in RL, you maybe initialize your value model from scratch. That doesn't necessarily work in NLP. In language model world, you have to use like initialize from like a supervised fine-tuned model or a reward model. Final takeaways. You need a million examples of supervised fine-tuning. This is where you get your performance improvements because it's helping you bridge all heterogeneous formats and chat formats that you're actually going to use your model for. Focus on prompt diversity from humans and then use synthetic procedures to explode the prompt space so you can interpolate. Preference fine-tuning, you also need roughly about 1 million examples of this. This is mostly about style and chat evaluations. DPO is much more practical than PPO for most cases. And again, human preferences are super expensive. Lean on LLM as a judge when you can. And finally, for reinforcement learning, you don't need as many examples, so that might change in recent days. It works well, but you have to be able to define the verifier, which is why it's mostly only been proven for math and code, because you can build automatic verifiers for those. Cool. And this is mostly a cherry on top. The big details is, can I do this without making accidentally an only math or only coder? I still want to preserve all these other performance. And that's it. Thanks.
Well, we can take a couple of other questions.
Yes. Yeah. Ah, there's a couple of variations. What I found generally is I think of one shot and few shot as also part of a template. So oftentimes what happens is after instruction tuning and switching to a chat template, people get away with the shots. Some people still also define a shot variant of it. It's not necessarily cheating, it's just making the task easier. I think the rule of thumb is if the task is too hard, the model hasn't broken out of noise, it's just not even performing this task.